Okay, so I wanted to do a quick video on molecularity, mechanisms, and how mechanisms are used in rate determining steps for elementary reactions. So if we take a look at in the PowerPoint where I ended, you see that reactions sometimes occur all at one shot or several discrete steps. And when we can designate these steps as such, then we call them elementary reactions, elementary processes, or you'll see me use elementary steps. So an elementary step means that it is a discrete step within the frameworks of a chemical reaction. And I have that written here, that the mechanism for a particular chemical reaction can have a single event or steps which give us what we call an elementary reaction. And the number of molecules or atoms, if they are in fact elemental, that are involved is what gives you your molecularity. And that is defined by the number. Unimolecular, that prefix, it's only one molecule involved. Bimolecular, that prefix will be 2. Termolecular is 3 molecules, and just due to the probability of 3 molecules or atoms all colliding with the proper energy, with the proper orientation, these are very, very rare situations. So, generally speaking, reactions can have multiple elementary steps, and adding the elementary steps together will give you the net reaction. So the way the question is going to be posed, we're going to show an example in a minute, but you're going to get the overall reaction, and then it's going to say that the proposed mechanism has 2-3 steps. And once you add those together and cancel things that are on both sides, you will get the net reaction that was given to you in the beginning. And if you do cancel out compounds during the course of this, then you are going to consider those intermediates. So in your textbook, on page 601 here, you'll see this practice exercise 2 in section 14.6. I'm about to walk through that one here. So the question tells us that we have a reaction, molybdenum carbon monoxide or hexacarbon monoxide and phosphorus trimethyl react to create molybdenum pentacarbon monoxide phosphorus trimethyl plus carbon monoxide. And this is again the overall reaction. And they propose that the mechanism is done in 2 elementary steps. And these 2 elementary steps are listed here and here. These are 2 separate, again, elementary steps. The first question in your textbook asks, is the proposed mechanism consistent with the equation for the overall reaction? Well, to determine that, we must cancel out anything that we find on both sides and then see if the overall reaction gives us what we have in the beginning. So the one thing that we can see is in both places is molybdenum pentacarbon monoxide. And once we cancel that out, we see molybdenum hexacarbon monoxide and phosphorus trimethyl on the reactant side, and then we see CO and this compound complex on the product side. So to that, we would say that yes, mechanism is consistent. Okay, question B asks us, what is the molecularity of each step? Remember, the molecularity is the number of molecules involved in the particular step. And we see in this first elementary step, molecularity is 1, or unimolecular. And in this second elementary step, we see we have 2. So the second step is bimolecular. That answers that question. And then the last question is C. It says to identify the intermediate. And remember, the intermediate are compounds that cancel out. And in this case, the only compound to cancel out is molybdenum pentacarbon monoxide. Okay, so there is an example of how to determine molecularity for a reaction when you have been given the elementary steps. Okay, so now let's move into discussion of rate laws for elementary reactions. And remember, rate law is rate equals K times concentration of reactants and based on their orders. If you look at molecularity, by definition, you will see that elementary reactions, we can assume the rate law and derive a rate law because elementary reactions rate laws are directly related to their molecularity. Again, elementary reactions rate laws can be derived based upon their molecularity. So in these particular cases, you see unimolecular has A turning into products, and we have a rate law that only involves A to the first order. Unimolecular, first order. Here's 2 bimolecular situations, which is we only need to worry about uni and bi. Bimolecular situations where 2A come together to form products. Then we have a second order bimolecular rate law that only involves A. And then here we have A plus B to give another bimolecular elementary step. Rate equals Ka times B. It's still second order, both of these. We won't worry about termomolecular reactions because, again, they are rare. So to define that, if we know the reaction is in fact elementary, then rate law is based directly on molecularity. First order gives you first order rate law. Second order gives you second order rate law. Again, how do we know that this is a first order rate law? It is based on the order that is assumed to be here by the concentration. Here is the second order because we have 2 things being multiplied by one another. Remember that the K value here, units, are different based on first and second. So again, this is first order, this is second. You have to be able to recognize that by looking at a rate law. Now we want to talk a little bit about the rate determining step. So let's say that we know a chemical reaction. We know its mechanism. We can determine then from that molecularity and overall reaction. But if we know the speed at which the reaction occurs, is it fast or is it slow? And by knowing the speed, we know the K value associated with the particular elementary step. Then we can determine the rate determining step and more specifically determine the rate law that we talked about up here given a multi-step mechanism. So for example, we have here step 1 and step 2 for a overall reaction. Now, if we want to take a look at combining the overall reaction, we see that oxygen is what cancels on both sides. And we end up with 2N2O, arrow, 2N2 plus O2. Again, this is the overall. we know that the intermediate is O. We also know that the molecularity of step 1 is unimolecular, and the step 2 is bimolecular. Now, when we are dealing with slow versus fast, this is where it should come into play that the determination of the rate determining step will always be based on the slowest elementary step. In this case, and in what you need to know for slow determining steps that happen to be the first step, you need to be able to then derive the rate law based upon the step 1. And we see that step 1 is an elementary reaction that only has one reactant. Therefore, the rate law has to equal this. It is first order, and we should realize that because we deem this to be unimolecular, so this has to be first order. Now, someone might ask, well, what about this 2 here? Remember, stoichiometry does not tell you rate law for an overall reaction. You can only determine rate law from an elementary step. And the slow elementary step is what dictates the rate. So the rate here is equal to K times N2O, realizing that there are 2 Ks here. Essentially, as soon as N2 is created, it is used up in this second step. So here we have the rate law for a multi-step mechanism that we know the speed is slow and fast. We were able to determine overall, we were able to determine intermediate, we were able to determine molecularity, and last but not least, we were able to derive a rate law based upon that. And that's what you're going to have to do. All right, so that's it for the scope of mechanisms that you will be responsible for on this exam. If you have any questions, always feel free to email me. Peace.